Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So welcome to this session on custom devices for research. My name is Scarlet Schwiderski-Grosche. I'm Senior Program Manager in the Microsoft Research Connections Group, and I work in the Cambridge lab in the UK. So we heard quite a number of quotes this morning, and I'm proud to say that our abstract, of course, starts with a quote. So that's manifested long before this morning's talk, so there's no previous discussion about this, but it's a quote by Alan Curtis Kay that he made in 1982, where he said, people who are really serious about software should make their own devices. And this is very much applicable to the session we want to have now, that very much the topic of our session. So in this session, we will discuss technologies that enable researchers to build complex, custom-made devices easily and very rapidly as well. And this is relevant in research areas like ubiquitous computing and Internet of Things. We'll specifically focus on a platform called Microsoft .NET Gadgeteer. That's a technology that has been developed in the Microsoft Research Lab in Cambridge over the last few years. But we will also, so this encompasses very much the hardware and the software aspect of the platform. We will also look at what we call the physical form factor, the 3D design of the encasing, looking at technologies like 3D printing, for example. Let me also say that besides the session, we have a demo tomorrow, so you will have the chance to look at the wonderful things that have been built in the ubiquitous computing domain. So do pop along tomorrow, have a look at the hardware platform and also at some of the devices that researchers have built with this. Right, so now it's my pleasure to introduce our first speaker, James Scott, who is a researcher at Microsoft Research in Cambridge. James has research interests in a wide range of topics, and ubiquitous and pervasive computing, also novel sensors and devices, technologies, mobile interaction, energy management, etc. He's got a PhD from Cambridge University, and he is one of the first people on the Microsoft .NET Gadgeteer team. So he was there very early on working on this project, and he will give us a broad overview of the technology. And then we'll have two talks later on from academics in this session who will show us, one designer who will show us how they've used Gadgeteer in their work, and then also looking a little bit about on the opportunities of such technologies and future outlook later on. Okay, over to you, James.
Thank you very much, Scarlett. I think I probably need to turn this on. Are we good? Yep, excellent. Okay, thank you very much for coming to the session. I know it's straight after lunch. I hope this will be exciting and informative. As Scarlett says, this first talk I'm giving is about this platform called Microsoft .NET Gadgeteer. So what is it? Well, if you think about the kind of devices that people build in the research domain of ubiquitous computing and other research domains, maybe using other keywords, there's a lot of value you can accrue from building custom devices, new types of devices that as yet aren't on the market. No one's actually selling them, but you use them to study new application domains. So there are some examples here. I don't have time to go through any of them, but there are huge numbers of examples here. And in the research group I work at, which is the Sensors and Devices group in MSR Cambridge in the UK, we build some of these devices. In fact, you can see MSR Cambridge written on one of them there. And we wanted to actually build a platform which allowed us to accelerate that work, to build devices more easily and more quickly. And this is the thing that, after a pile of different iterations, has ended up being called Microsoft .NET Gadgeteer. So if we think about why you want to build custom devices, what does that let you do, and what do you need from them? They're the kind of things that need to be developed quickly by a small team, a group of researchers, but they're different from kind of prototypes, which could kind of show off a concept, but not really take it to the point where you can give it to an end user and have them use it. So we're talking about devices that are fully functional and usable devices that can be deployed in the wild, and also could be produced perhaps in some sort of quantity. You don't just want one that might break, or you have a user study of n equals 1, it's not so good. You need 10, 20, 50. So this motivated the platform we built. There are lots of existing tools in the space. I'm sure some of you are familiar with these. Arduino, Fidgets, even Lego Mindstorms is an example of something that can be used to build custom devices. I'm happy to talk through the differences between Gadgeteer and any of these in questions or offline, or you can read there's a paper on Gadgeteer and so on. But let me tell you first about the platform, and then we can have a comparison point. So here's, let's jump straight into a sort of demo. I mean, I'm afraid it's not a real live demo, but there's a little kind of set of slides here for you. Let's imagine what would it take to make a handheld, a completely custom handheld video game device in just 24 hours. So you start with some hardware modules, right? You kind of say, well, I want my game to have some sort of input, maybe a potentiometer here, some output, a display, a button, something like that, and a processor which might run some logic, and some way of powering it. Then you need to write some software, right? So here we got some C#. There's a snippet of software here. You might put that together. In this case, it took us maybe 5 hours to kind of program a little game engine together. Then the next thing you need to think about is, OK, so I need to actually turn this into something real, something physical that can be held, to be a custom device. So to do an enclosure design, here's an example, might take something like 3 hours in a package like SolidWorks or so on. And then you can use rapid fabrication technologies like 3D printing to make it real, print it out, make it real immediately. Here is the output of the 3D printer we happen to have in the lab with a few of the components put on it to illustrate. And then assemble it, actually add those physical components, put it together. Maybe that takes 20 minutes. And in the end, maybe you have something like this, and you can actually play Tetris. So we've gone from kind of an idea to, in 24 hours, having something physical in your hand that you can really try interacting with. And immediately we think, well, this big knob, is it actually the right way to control the left and right? Maybe we should use other mechanisms. Maybe we should add sensors. Maybe we should network it. So, this is just the first iteration. Of course, it's a bit of a toy example, too, of many iterations. But the fact that you could iterate in just a day and then another day and have a completely new device in hand, it lets you accelerate the kind of research. This isn't going well for whoever's playing here. So this is what we try to build in .NET Gadgeteer. And really, there's kind of 3 different threads to the platform. There's the hardware, the software, and the physical design. And they're all as important as each other, right? A custom device relies on all 3. And so now I'm going to talk through those kind of in order. So starting with the hardware. Gadgeteer hardware is built around a mainboard. So every Gadgeteer device has a mainboard, which has a processor, an ARM-based processor, and a number of different sockets, standard sockets that you can plug little ribbon cables into, that modules can plug into. So to this mainboard, you need to add some modules, right? And of course, the value of the platform depends on, well, what range of modules are there? What can I build, right? And so there's a lot. And actually, I should say all of these things in this section that you can see, these are all actually on the market today and not made by Microsoft, made by third parties. So this is kind of indicative of how far the platform's come. So there's a whole pile of sensors, accelerometers, gyroscopes, pulse oximeters, GPSs. There's communication modules, cellular radios, Bluetooth, Wi-Fi, Ethernet. There's lots of different ways to get user input in or output to the user, ranging from big displays to little LEDs, and there's more actually I can think of that aren't even on this slide. There's modules around to power the device. Any Redboard here provides power, so that we have Redboards including battery modules. But also things like relay modules. So you can control a 240 volt or 110 volt output using this. There's storage and audio modules, so SD cards, a music output module. And somewhat most importantly, in a way, there's modules that really are just designed around extensibility. So that themselves have no direct outcome, but allow you to very easily make new modules. And we find that in our uses of Gadgeteer, maybe you're building a project and 9 out of the 10 of the modules are off the shelf, which is great because you don't have to worry about them. You just buy them, you use them, they're the same as old. But there'll be this one new sensor or one new thing that you wanted to do, one new user input that you wanted to try out. capacitive touch, who knows, something like that. And so here's where modules that are just exist to allow you to very easily extend the platform come in. So each of these sockets, here's a picture of a main board. And the kind of magic of the hardware side of the platform is each of these sockets is slightly different. Each exposes a different set of pins that the processor has. And we kind of encode this functionality of the sockets into a series of letters. So every socket can support many different socket types, each of which is a letter. And so this is what the formal specification, which is an open specification of the platform is. So for socket type A, you have 10 pins on the socket, as you can see. And pin 1 and 2 are power. Pin 10 is always ground. And then for socket type A specifically, we say that pins 3, 4, and 5 need to have some analog input functionality. So if you have any sensor that just gives you an analog reading, this is something that you can make compatible with Gadgeteer socket type A. And we can now look at the whole range of different socket types that are defined so far. And of course, this itself is extensible. You could define new socket types as new processor buses come out and become prevalent. That's actually a fairly slow process. So in the year and a bit that we've had this socket types definition, we haven't actually added one yet. We haven't, no one said we really need this new one that wasn't already there. But the nice thing is, as an end user, or even as someone who, as an end user being the researcher building devices, you don't need to care about that. You just look at the letters on the module and the letters on the main board, and you match them up. It's like building IKEA furniture or whatever. So, we can abstract all that hardware knowledge away. If you don't want to be the hardware hacker, then you don't need to be. So that's the hardware. From the software side, we try to aim for something similarly easy to use and to build stuff with. And we're aiming here to provide an experience that's not like programming a PIC or writing TinyOS code that's really low level, but to provide something much more like writing an app for a phone or writing an app for a PC, which is a very much higher level programming experience. And to do that, we leverage something called the .NET Micro framework. So this is a subset of the .NET framework, which I hope you all know about, but it is a subset that runs directly on the processor. So there's no OS running on this little ARM processor. There's just the runtime for .NET Micro framework running. But that means that you can program in C# and Visual Basic. It means that you get interactive debugging, so you can put breakpoints in, you can watch the variables, you can edit the variables on the fly. All of these things that we take for granted when programming for the desktop or phone, you can have as well in an embedded platform. And so what .NET Gadgeteer adds on top of this micro framework, which is an existing product, is a set of libraries, a graphical designer, which I'll show you in a second, and a framework that makes it really easy to extend the platform and add a new module, add a new mainboard. So here's what you see when you start a new Visual Studio or C# Express or Visual Basic Express project. So you start a new Gadgeteer application, and you see this view, which is a designer view, which allows you to bridge between the hardware that you've created and programming the software. So it'd be better to demo this, right? But you essentially drag in the modules from this list on the left, and they come in and show you images of these physical modules that you have. And then you specify, OK, this is how it's all connected together. And in fact, it will connect it for you automatically if you want anyway, because it knows the constraints that that socket will only plug into a type F, and here's a type F over here. But one of the things that you're doing here implicitly is you're giving everything a name. So if you have more than one button, more than one screen, you better have a different name for it so that in your code you can later refer to it and tell it something. So each of these things under here, SD card, camera, and so on, that's a name that you can modify if you wanted to change for your program. The code is, in this case, it's C# code that I'm showing you. Some of the differences with kind of existing embedded paradigms, it's very event-driven. So we use a dispatcher model, for those of you who care about that, which means that everything that you, so a button press, for example, arrives as an event that you handle, and then you can maybe kick off requests that will later on come in as events. The nice thing about a dispatcher model is you don't have to worry about race conditions, deadlocks, all of that kind of stuff, which I might otherwise have to think about. It's also much more, you can easily access a lot more complexity than you can with a kind of wild true model, which is something like Arduino uses by default, because you can have many different kind of chains of control happening in parallel. The other thing that you can see from this is that for each of our modules, like camera, we have essentially said, OK, you need to not only provide the hardware, the physical camera, but you also need to provide essentially a device driver for it. So that the end user doesn't need to know, oh, well, it's an I2C control interface, and I need to talk to address whatever it is and send this byte. You should just be able to say camera.takePicture, and this little driver knows how to translate that into the actual underlying command and go and do it. And later on, throw an event, picture captured, where you can receive this thing as a picture and do things with it at a high level. So this, for example, is all the code that you need for a digital camera that takes a picture when a button is pressed, puts it on the display, and also saves it to an SD card. We also have, if you install the kind of template, the builder templates installer for Gadgeteer, we make it really easy to make a new module. So I could go on at length about all the different steps there, but the key thing is that you instantiate this new module project. You put in your little bit of driver code that says, OK, when I get told to take a picture, then send this I2C command. And when you compile it, it generates an MSI installer for you. So all that stage of kind of, OK, packaging up my little driver and making it accessible for someone else gets kind of taken care of for you. You get this MSI, and if you give it, which is a Windows installer, and if you give it to someone else, then it will just appear here in the list on the left. So when they start their new Gadgeteer project, they've installed your little device driver thing. It appears as a first-class citizen in the list along with all the other manufacturers. So the third aspect of the platform, which is, as I said, just as important as the other two, is support for physical design. And the reason why this is important is you might build something like this. Here's our digital camera example that I showed you the code for earlier. But it ends up looking like a pile of spaghetti, right? Like an octopus or whatever you want to call it. That doesn't look like a digital camera. You can't give it to someone and ask them how they would interact with it as a camera, ask them to use it, which is the whole point of custom devices. So, what happens? How do we allow people to very quickly and easily box it up? This is actually a little cardboard kind of net that you can quickly fold together. If you come to the demo session, you'll see some of these. And if you give me a room full of students who've done any sort of programming, so like 16-year-olds, in an hour, I can have them each holding a camera and loving it and thinking this is the best thing ever. So the way we promote being able to build those form factors easily is to have a set of hardware design guidelines for the modules that standardize things like the mounting hole layout, the sizes of them. Based on that, you can use things like standard mounting hole platforms. And we kind of found that Tamiya already, who's familiar with Tamiya? Anyone spent any pocket money when they were a young kid on Tamiya stuff? Yeah, I spent a lot of my money on them. So basically, they sell little robot platforms that, as a teenage kid, you can put together, and it's fantastic. But now I get to buy them and expense them because they just so happen to fit Gadgeteer modules. So yay. And you can very quickly build stuff together using them. And the next step on from that, right? We can, that's all very well. You got this little plug board. We can do even better, right? So think about 3D printing and how we access those kind of things. So we also have 3D models of all the hardware modules that are available on the market today, and that allows you to use CAD programs like SolidWorks to kind of very quickly and easily design cases that you can use rapid fabrication tools to print. So I'm just kind of skip on this because I know I'm running out of time a bit and I want to leave lots of time for other people. But we've got essentially a tool that makes it very easy for people to make laser cut cases where you can kind of add and position the 3D models in them. And it will automatically do things like print mounting pillars or cutouts or holes if you're doing laser cutting and you need to mount them that way. And the cutouts like this, so that you have this model and it's annotated in a way that allows you to very easily kind of build 3D cases. And so here's a kind of example of a laser cutting enclosure. Another fabrication technology, I said laser cutting, also 3D printing is a really interesting thing. So again, you can do the same thing here, use a slightly different template which is optimized around the capabilities of things like 3D printers, and again make very custom but high fidelity enclosures. And if this is the kind of thing I can make with a very simple box with SolidWorks, because I'm no good with it. I've never had any training in it. If you ask our kind of one of the designers working in our group, he comes up with absolutely beautiful objects that look like this. And we're going to see some more examples of that in a little bit. So let me kind of close the loop a bit and say what we've used this for, right? We built this platform. We built it as a tool for ourselves, and we've also made it available for other people by standardizing it. But what have we used it for? And there's a whole pile of different papers. I want to just focus on a couple of examples. There's a project called PreHeat, which I presented at UbiComp 2011, some of the co-authors in the audience here. And the idea here is to do home heating using occupancy sensing and predicting when the space is going to be occupied and just heating up just in time. So it's kind of an automated system that uses motion sensors and occupancy sensors. A couple of things Gadgeteer allowed us to do for this project was, first of all, iterate quickly through the form factors. So, from the thing on the left, which is a little cardboard cutout with just the motion sensor on, now we realized, okay, we actually want a UI, and we really need to 3D print these things because the cardboard isn't going to last for long. And then just iterating through the designs of the 3D printed cases was something that was very quick. It allowed us to achieve a working prototype quite quickly. Also, so here's my house. This is the PreHeat system installed in my house. And what we then did after we had something that we thought, yes, this works, it's got all the buttons and knobs and the sensors in the right places, is we just turned the 3D printer on and ran it for a month. And we made 50 of these things and deployed them in various different places. And these devices have actually been up and running in my house for 3 consecutive years, controlling my heating system, saving me money. Yay. So the value of Gadgeteer here was that it is in this scaling of being able to say, okay, well, now I built one. Now I need 50 of the same thing, and being able to scale up to that. Another example of this in use that was at a studio at TE. A studio is kind of like a hands-on workshop that the Tangible and Embedded Interaction Conference has. And so here we were able to get people to very quickly move from a kind of sketch to a 3D printed demo. And so the workshop was 2 days before the demo session of the same conference. And by having a 3D printer there and running it in the middle day, we were able to have people demo what they made in the workshop at the demo session alongside other demos that people had been working on for 6 months, a year. And the prototype fidelity looked not too dissimilar. I mean, the ideas weren't maybe as good because they'd only been thinking of them for 20 minutes over lunch, drinking the wine and Madeira. But the fidelity was there. So the final little bit of this talk I want to talk about is how, a little bit of thinking about how we got .NET Gadgeteer out of the lab. So, there are many kind of prototyping platforms that various groups have built, and I'm aware of, and they're very good. We kind of tried to take the extra step here because we've had so much interest and make it available so that hopefully all of you can go and build on this as well. And so to do that, we've got a couple of different websites. There's gadgeteer.coplex.com, where all the source files for the software that runs on the embedded devices, that's Apache license. So go and play with it, do whatever you want with it. It's completely open. Similarly, for the design files that I already showed you about the specifications for what it means to be a Gadgeteer device. We also have a kind of more end-user-focused site, which is netmf.com/Gadgeteer, which is where there's an index of all the different hardware from various different manufacturers. So I should say we ourselves at Microsoft aren't building and selling this hardware, right? We're not set up as a company to build and sell stuff on that kind of scale. But I think there are kind of 9 different manufacturers now selling something like 80 different hardware modules and 7 different mainboards, if I remember right. But the number is kind of continuously growing. And you can now actually go and buy it in a whole pile of places, so SparkFun, Mouser, and Amazon. It always feels kind of weird giving this because I end up feeling like a salesman instead of a researcher. But the thing is that I go to these websites too, and I buy this stuff, right? So we built this platform, we put it out there, but we did that because it's useful to us, and we go and buy it ourselves. So like I say, we hope it's useful for you as well. So last slide, huge thanks to a whole pile of teams inside Microsoft that have made this project possible. I didn't even thank my co-authors on the first slide. I hope you caught their names. Some of them are here. But Microsoft Research Connections, who is hosting Faculty Summit, and through Scarlet, has been hugely impactful in terms of outreach activities around this, and various other groups in Microsoft who have helped us out. So thank you very much for your attention. I don't know how much time I have for questions, but I'm...
No, you're well in time.
Yay,
okay.
Very
good.
Great.
Thank you very much, James. So we have time for a couple of questions before we move on. Any questions for James at this stage? We'll have a longer Q&A session at the end. May I ask who's here who has a designer background, perhaps, a non-computer science background? Are there any designers besides the one I know? So that's an
2.5.
interesting aspect of the work that we will explore later.
Who's a computer scientist, on the other hand? Are we going to see lots of hands? I want to know what the rest of you do. Check your email.
There's a question here.
Hi, I wonder if you know of any universities that are using this and would be computer science or maybe computer engineering if they've developed projects and stuff.
Maybe we should take that after we hear the next couple of talks, which are from people who are at universities who've got the platform and are making use of it. But yeah, I'm happy to talk about that.
Yeah, and you will view the work tomorrow at the Demo Fest, so you're presenting some of that work. Any other questions now? Otherwise, we'll move over to the next speaker.
Yeah, please do come by and see the demos. It's, you know, seeing the slides is a very dry way of experiencing this platform. It's lots of fun.
Okay, thank you again, James.
Cheers. What do you want to?
Right, now it's a pleasure to welcome our next speaker, Bill Gever from Goldsmiths University of London. So Bill is a professor of design and he leads the Interaction Research Studio at Goldsmiths. He has worked on interesting projects. I have to read this off because I'm a computer scientist and it doesn't come natural to me. So he's worked on cultural probes to the use of documentary film to help assess people's experience with designs. Hopefully he will have time at some stage to tell us more about that as well. But among other things, he has produced prototypes that have been deployed for long-term field trials. And the talk he's giving now is in this space.
Right.
Bill is a fellow of the Royal Society of the Arts, a member of the Chi Academy, and he's got a PhD from University of California in San Diego. So over to you, Bill.
Yeah. Is this mic on? Okay. Thank you. Right, so what I'm going to do is talk about a project that we're kind of finishing up right now, in which we used Gadgeteer as a platform for doing a large-scale deployment of about 60 devices, shown here, to people's homes in London for a period of months. And I should say that I feel a bit weird being the only author. It's a project that's been pursued by a fairly large number of people in my studio over the last period of time, and they all deserve at least as much credit as I do. So before I begin talking about the project itself, I thought I'd introduce a bit of the work we do because we're perhaps a bit unusual for this kind of event. Basically, I more or less lead a place called the Interaction Research Studio. We're in the design department of Goldsmiths in the University of London. And we do research on interactive technologies as designers, from a designer point of view. So our research is design-led, but we're also very interdisciplinary. People in the studio have backgrounds in product design, largely interaction design, also the social sciences, both including sort of empirical social sciences, and increasingly we're engaging with STS theory, and we also have some fairly well-versed technologists in the studio as well. And I was noticing earlier that the order in which I have these fields is kind of indicative of who we are. There's about 12 of us in the studio. We're staff researchers. Everybody's on contract. We have some PhD students, but the core work is done by people who've been working with the studio for a number of years. We have a very strongly developed culture, and I like to think that that shows in the work we produced. And we also have a really great view of London if you ever want to visit. So we kind of pursue a certain style of research. We do practice-based research, and we do our research by designing and producing computational devices that are often in the form of kind of appliances or bits of furniture and so forth with computational elements. The things that we produced are very highly finished, both from a technical point of view, but also a design point of view, and we almost invariably release them for long-term field trials in the wild for periods of months and sometimes years. The other thing about the work we do is it tends not to be task-oriented. We tend to design things that are very open-ended, that kind of afford what we've called ludic engagement, kind of a playful engagement. So that what we're trying to do through our design is create situations and give resources to people to interpret for themselves, rather than producing tools that they use to follow preset ends. And I'll show you a few examples which will hopefully make that a bit clearer. So this is a few of the things we've developed over the years. And just for some examples, the one on the top left is called the photo stroller. It's a trolley that shows an endless stream of kind of an endless slideshow of flicker images controlled thematically using a hand-held controller on the front of the device and also tuned and detuned for relevance to various themes. And we deployed that to older people in a care home in the north of England, where it actually is still existing. The piece in the center, the prayer companion, is a device that shows a stream of text drawn from RSS news feeds and social media sites as a resource for the prayers of intercession of a group of cloistered nuns in England. The piece on the top right is called the plane tracker. It uses the aerial to pick up transponder signals from passing aircraft and recreates their flights using a hacked version of Google, so that sitting in your front room, you can kind of travel along with the airlines, sort of hitchhike along with the airplanes flying outside your house. And there's more, so much more. As I say, we deploy these in long-term field trials, often into people's homes that we recruit, and also in more specialized places, such as the care home or the convent, as shown on the top. So again, computational devices, highly finished, long-term field trials, not task-oriented. All of this amounts to what we have characterized as a form of third-wave HCI, in which the concern is really about designing for everyday life, in which questions of emotion and aesthetics and politics and spirituality and all that becomes as important to the success of a design as any other factors. And we're trying to find ways to work within that space. So the project in which we produce these devices is called Legible Landscapes, and it really came about because we became interested in a funding possibility through the European Research Council, which gives very large open-ended grants to people. We thought we had no chance of getting one of these grants, so when we wrote the proposal, we said that we just told them what we thought we wanted to do. We didn't spin it to try to get the money. We didn't think we had a chance. We just said what we thought was important, and to our surprise, actually got the grant funded. So what we said we wanted to do is to advance this notion of third-wave HCI conceptually, but also empirically. One of the key things we thought was that instead of building one-off prototypes, most of the things I've shown you, I showed earlier, are just one-off prototypes that we've made. We wanted to try moving towards batch production of multiple prototypes so we could deploy them to multiple people at once and look at the varying ways in which they orient to and interpret the things we make. And we also wanted to, in a sense, get serious, to start addressing domains of acknowledged importance. And in the first phase of the project, certainly we're trying to get in the ballpark of concerns about the environment. And we also wanted to address another issue we think is important, which is about the legibility of sensors used in systems like this, which I will expand upon briefly later. So in opening the project, we knew that we wanted to build in a domain. We had no idea whatsoever what we wanted to make. And we have certain kind of tactics we take to try to develop design ideas. We started in this project by pursuing a number of physical tests around the studio, making odd little paper weather vanes, hair hydrometers, using thermochromic ink to see whether it would evaporate and make it nice patterns on the side of bottles, all to try to attune us to the notions of the kind of microclimate of an indoor space. We also pursued a number of project reviews in which we looked at numerous arts and design projects vaguely in the area in which we were interested in. We ran a Storybooks probe study in which we worked with a children's book illustrator, Alexandra Antonopoulou, to design a kind of storybook for adults, which took as its premise that the protagonist had been shrunk to the size of the pea and was now wandering around their home. And the book was designed to be open-ended. We invited participants to finish it themselves using photographs, sketches, and the like. And all of this kind of set us out in helping us understand the values and the feel for the people might take to the systems we deployed in their home. At about the same time, we also started playing around with the kinds of sensors we might use in a system. And we worked with a guy named André Knorig from Berlin to build a very starting sensor kit for trying to look at various things going on in the home. The sensor kit shown on the upper right, it was meant to be functional, no more. And we deployed it within a few of our own homes within members of the studio. And we found a couple of things that sort of surprised us. So the first thing was that the systems were experienced as incredibly invasive. So despite the fact that the people who had the systems had worked on developing them, they found having these sensors in their homes to be invasive, intrusive, and really very annoying, actually. The other thing we found is that they were more work to produce than we had expected. They were really they took longer than we wanted to make. So the second problem, anyway, was addressed when we had a visit from Nick, who brought along the kind of nascent Gadgeteer system, showed us some of how it worked, and also showed us a little gust sensor that he had built, shown here, that he had built the hardware and software for, and also made this little enclosure. And when we saw that, we were pretty sold that Gadgeteer looked like a really interesting system to use, and that is indeed the system we developed our following pieces with. And I'll go back to Gadgeteer really towards the end of this talk. So despite the fact that we'd done all this research, we really didn't know what we were going to build still. So we did, as we normally do, we started generating design workbooks, which are collections of images that either propose possibilities for design or do studies of certain issues, work up ideas. We tried to build a very wide design space through these workbooks. And this one was possibly the widest ever. We developed 5 different workbooks, each with potentially about 100 pages. And much work ensued that I don't have time to tell you about before we sort of focused in on a few core proposals. So this one is for a micro gust sensor that would look at tiny drafts around the house and amplify them to bring them to people's attention. This one is a temperature tape measure that would allow people to compare the temperatures in different parts of their home. A third was a color picker that you would point to look at ambient colors in the home to try to understand the kind of aesthetic atmosphere of the home, I suppose. And then after that, a lot of other work happened. I have to go through this very quickly, in which we basically took these initial proposals that set a course for us and actually developed the first prototypes of the devices that we went to produce. So these are the 3 devices that we produced in the end. The one on the left is, again, called the temperature tape measure. It's got about 2.5 meters of ribbon cable on it, actually cloth-covered ribbon cable, which at each end there's a heat sensor put into a special casing that allows you to hang it in various places in the home. It's also printed along the way with stripes of layered thermochromic ink that changes color depending on the temperature so that you can see gradients of temperature from one end to the other. The piece in the middle is called, wow, this got really screwed up, didn't it? Sorry, I just noticed that. It's called the light collector. It's got a kind of copper-leafed bowl on the top that collects light to a light sensor at the bottom of the bowl and then recreates the ambient light it's seen using a LED on the side so that it lays down a strip of the current color every 5 minutes, and that gets built up over time down the screen so you can see the changes of light over about a 2-hour period. And the one on the right, which is not called drafts, it's called the wind tunnel, is basically has a little gust sensor built into the top of that tunnel, which measures the gust and then amplifies it using a fan to blow around a stylized kind of forest in the greenhouse below. And those are the 3 devices. They're incredibly simple, as is much of our stuff, but they were meant to draw attention to various things going around the house. There's also a few shared features across the 3 devices. Each has a last day button that allows you to rewind through the last 24 hours of data so you see the tunnel blow on and off quickly to show you how the wind was over the last 24 hours, or the kind of pattern on the light collector goes up so you see the way that light has changed over the last 24 hours and so forth. They also have a lull button, which is like a sleep button on an alarm clock. If the light bothers you or the wind tunnel bothers you when you're trying to sleep, you can hit the lull button and the display will turn off. The data is still collected for the next 8 hours. And then 8 hours later, it turns on automatically. And they're all 3 are also Wi-Fi enabled, so we can send the data back to, we send it to a service called Patch Bay or Patch Bay, whatever it's called. So we can collect that data and make it available to our studio for other uses. Again, the point of this was to batch produce the things. This is a very new endeavor for our studio. We ended up making 22 of each of the 3 devices, almost entirely in the studio itself, where we used our object. We have an object printer that we used, also a laser cutter. We have a fairly well-equipped workshop, and Gadgeteer was really at the heart of being able to do this work. And moreover, beyond the devices themselves, there was other design activity that went on around this deployment that was actually fairly substantial as well. We developed a PreWorks website initially to give information to participants. Then we opened a blog to allow us to communicate back and forth with the participants. And finally, we started publishing historical data about their sensors so that they could get access and share it amongst each other. We also produced a lot of print material that included everything from a quick start guide shown on the lower right, which people could use in their homes to understand the devices, and significant moment forms that allowed them to report things they noticed with the devices they thought were interesting, and a host of other items. And so now what I'll do is quickly go through some of the observations we've had. Some of these, we've kind of done a staged deployment. The devices have been out for as long as 6 months in some households, slightly shorter for others. And I will show you some of what we found. So we have about 20 households working with us that we recruited using a variety of flyers, blogs, newsagents, and trees. We visited about half the people in their own homes and showed them the devices. Others we distributed in our studio or in cafes. And almost always the first thing when people opened the box and saw the devices is kind of an immediate appreciation of their aesthetic quality and intrigue into what they might be like. After a few weeks, we started making sort of spot ethnographies of some of the people. We're using a variety of means to get at what they think about the objects, but I'll report ethnographic data here. And we found that, slightly to our surprise, a lot of people were drawn to trying to use the devices for utilitarian aims, almost as they would use draft detectors or ways of or kind of comparable to home energy meters. And so they tried to look at where heat was escaping the home or where drafts were coming in to more or less success. But this really merged with more exploratory activity, ranging all the way from trying to understand the different microclimate of the home to really playful activities like having a game where they tried to see who could heat up the sides of the temperature tape measure quickest. And hanging it, shows the temperature tape measure hanging on a stairwell in a way that's quite awkward, but allowed them to really explore their home in a different way. I have to admit, though, that after several months of this, we started seeing signs that people were finding the experience of the devices rather underwhelming. And there's a few quotes here. Probably, in a way, the most typical and damning is the last one where they said, well, they've become normal. It's just part of the furniture. We don't really notice them. And we started feeling a bit depressed about how the whole thing was going. But we started seeing or noticing or clinging to signs that actually there's more going on than appears. So first of all, the devices appear to be very comfortable in a domestic environment. And over time, many of the devices find a place in the homes that they're in, and people are really happy with them there. They remain objects of aesthetic appreciation. This is an example where somebody's actually painted an oil painting of one of the devices, in part because he thought it was nice. For some, ritual uses have developed. So, for instance, one person told us that they always hit the replay button on the light collector because they like going through and seeing the sunrise that they've missed, and so forth. And there's numerous examples where people have shown that even though they're not kind of the thrill machines they had thought they might be, that they appreciate having in their homes. The other real win for us is this notion of acceptability. I told you how uncomfortable it was having sensors in our own homes. What we found with these devices is that people place them in spots that really are quite private, in their bedrooms, in their living rooms, and so forth, where they just wouldn't place them if they were nervous about being spied upon. And the signs of suspicion that we've gotten in other deployments using sensors where people think that there might be something else going on haven't occurred in this one. And we think it's because there's output very local to the input that makes the operations of the sensors very legible and accountable. And I think that's actually in itself a real win of the project. So this is right next to somebody's bed, for example. The other thing we've seen is people talking about the sensors as having this kind of weird presence in the home. One of the more striking ones is somebody saying, well, we have 2 rabbits, and we don't understand what they're up to either. The sensors are kind of the same. We like it. It's nicer to have something around that's enigmatic, and so forth. And so, read it as you will. The last thing is we're beginning to understand that this is a very long-term experience. We've had numerous comments about people talking about how the light changes over the seasons and how these things make them aware of that, and in general how some of these devices are making them aware of their homes in ways they haven't been. So we often think of our devices having a kind of trajectory of appreciation where we can think about how engagement changes with time. It's not unusual to see this kind of beginning curve where people are really excited in first deployment, and then a few weeks later they start to lose interest a bit. And that's one of the reasons for the very long-term deployments we do. Now, there's several follow-ups to that. Often with our successful pieces, that engagement continues at a lower level for a very long time, with ups and downs, but people will engage with some of our things for months or years. We've had a few where after that initial peak of excitement, there's been a kind of death spiral into a lack of engagement. That's known as failure in our terms. I'm beginning to think with these devices that we're looking at yet another pattern in which the engagement drops to a much less level than with some of our devices, with occasional peaks of interest when things are noticed that provide particular insights. But time will tell. We will see. Let me just say a few words about using Gadgeteer in all this, because in some ways this is the topic, isn't it? So there's a number of achievements, we think, that we've made in using Gadgeteer. It's allowed us to make a number of achievements. We managed to go from knowing nothing about Gadgeteer to developing 60 deployed devices in 6 months. And moreover, there are 3 different devices using different technology mappings. They include real-time display, SD card, storage and replay, transmission to patch bay, et cetera. We actually had them all running with battery power for a while, that wasn't reliable enough to be released. And we think that's pretty cool. Most of this comes from our creative technologist, Mark Hounstein, who's a real fan of the Gadgeteers. His background is not in computer science or engineering. He's had experience with Arduino, Visual Studio, C# and so forth. And he found that picking up Gadgeteer was really easy and allowed him to do things very quickly. At the same time, we hit Gadgeteer to kind of, skipping a slide. There are a few things he really points to that he likes a lot. One is the modularity of the hardware and software made it very easy for him to play around and knock up the designs and different variations of the designs very easily. He found that, he says that writing the software is like writing software for a PC. He really sees that distinction and appreciates it. He liked various of the features, like IntelliSense and on-device debugging and so forth. So again, he valued using Gadgeteer quite a bit, and he has extensive experience, at least with Arduino. We did have problems in that we started working with Gadgeteer when it was still in beta, and a lot of the designs focused around the beta components. And when it actually became a commercial release, this caused us real difficulties. So the components released by GHI Electronics were larger, and they didn't include all the components that we wanted to use, so we ended up having to design custom components, go around and beg Nick for every beta version he could find, and so forth. So this is an example of having to redesign the button for the last day function because the button that we could get commercially was too large, and we went through several iterations and ended up basically getting the PCBs made and then having to put all the components on in-house, which was okay, but not great. But that's kind of minor. That's a historical detail. There's a few other issues that Mark suggested were kind of more maybe intrinsic to Gadgeteer and thinking about how we might use it in future batch production deployments. So first of all, he said that though the programming environment is great, it's easy to forget that you're designing for an embedded processor. It's got a very complex structure of management compared to Arduino and so forth. And probably the key one is that although Gadgeteer is great for doing prototypes, when going to batch production, all the modularity, the cables and so forth actually make it very unwieldy to use. So this just shows one of the devices, the light collector, kind of stripped apart to the components. This shows the wind tunnel as it was finally laid out, and you can see there is a lot of ribbon cable all kind of stuffed in there. All the components are jammed in there, and the very things that make it powerful as a prototyping tool makes it rather unwieldy for batch production. But in conclusion, we liked it, and we'll use it again, and we're very happy that we got to use it this time. So thank you.
Thank you very much, Bill. And as I mentioned before, you'll be able to view those devices tomorrow at the demo fest at our Gadgeteer table. So we have a couple of minutes for questions for Bill before we move on. Are there?
Are you planning on taking the devices out of the homes at some point and seeing the reaction that people have to them not being there anymore as an indicative of how used to?
Yeah, we might do. I mean, actually, we're tending to think of this as a very long-term trial. So, because we think I mean, there's a couple of things. So it's a little hard to get at the user experience, but one of the telling incidents for me anyway was we went into somebody's home and they said, "Oh, this is going to be a bad result for you." But then as we talked to him, it became clear that what he meant is these things didn't speak to his environmental concerns very clearly, but that but nonetheless he'd grown very fond of them in his home. And we offered to take them away, and he didn't want us to. So in a way, people do grow attached to them. At this point, we're planning to leave them there for duration, because we'll see what happens. So we'll see where that goes.
Yeah. Some question.
Hi, I'm Frans Maurer. I'm heading the game research lab in the University of Tampere in Finland. Thanks for the presentation. We actually are starting a new project that is dealing with hybrid digital physical playfulness. And I really appreciated your methods because I see some similarities in our approach. Could you comment a bit more about these playful behaviors that you witnessed in your field trials?
Well, this is not, I mean, in a way, these devices were not made for playing quite so much as some of our previous ones. But we did actually, we did make them to explore the home's microclimate. And so the playful behaviors we see varied from trying to find the hottest and coldest places in the home or finding where light would be particularly interesting or unusual to some of the things I showed in the quotes where people were heating up the ends of the temperature sensor or I don't know, trying to blow on the wind sensor and so forth. I think what we see in general with the kind of playful behaviors is that when we build things that are really open-ended, where the purpose is not entirely clear, people will explore them for a variety. People will explore them all the way from very kind of utilitarian reasons to the more silly ones, and in between is this area that I particularly like, where they're using it to explore possibilities and values that they haven't really been aware of before. So that's a longer conversation, but it's nice to meet you.
Hi, Bill. You mentioned that these people had some ideas in reply to the objects. Are you going to make those ideas real, or you're just going to leave them as ideas? Like the playback of the light over a whole year. That could be a different...
Yeah, well, actually, in response to that, that's one of the reasons we designed the website as we did. So right now, we are capturing all the history of the devices and publishing that on the web through interactive graphics. And yeah, that's what we're doing. Now, personally, I think, yeah, we could be making those real as objects, but we're not at this point.
Okay.
Thanks again, Bill.
Thank you.
Right, so our last speaker is Albrecht Schmidt. He is Professor of Human-Computer Interaction at the University of Stuttgart in Germany. Albrecht is interested in HCI beyond the desktop, especially user interfaces for mobile devices and cars. Albrecht has a PhD from Lancaster University. Over to you, Albrecht.
Thank you very much. Does this work? Yeah. So the session is called Custom Devices for Research. And when writing the talk, I figured out I think the interesting part is going beyond research. And I think Bill just showed there is some tricky stuff ahead if you go from 3, 5, 7 to basically a larger number. But I think that's a really worthwhile thing to look at. And so we'll talk a little bit about custom devices for research, but then the major part of the second half is really looking into if we take it really beyond research, if there is some new model ahead. So I will talk a bit about hardware as opening opportunities. And I think we have seen this from the UbiComp research from the very beginning. I think if you look back, if the people at Park wouldn't have had the ability to build hardware, that research would not have happened. And if you look back at a lot of UbiComp research that happened over the last 10 years, and by sort of, I think, the last 5 years also, if you look in the CHI conference, a lot of things that were picked up, and I think there's somebody sitting at the back who had last year some media attention for building new stuff and showing it at CHI. So I think the moment you build stuff, it captures people's imagination. And it was flexible displays or sort of other stuff. You really get people thinking beyond what they have the moment you build hardware. And I think the UbiComp stuff at Park was sort of the first one pushing this really in a wide way. And there was much more. And the other direction we have seen over the last years, tangible interaction. Again, sort of, it's not, you can't really think of tangible interaction without building the hardware. And there are some examples of stuff we build. And I put them up here because if you look at them now, the amount of resources that went into building those things is just sort of crazy. Basically, how many hours you need to build those custom devices the moment you start from scratch. And obviously, at that time, we thought it's worthwhile to do it in a way, to really spend that time, spend that effort in building it. But in the end, a lot of the effort you put in is after you have built a device, there's very little value to it, to building sort of a new hardware platform for every device you build. You don't get the credit for the hardware platform. And also in contribution to research, the hardware platform doesn't really make much of a difference. It's really the experience you create, the concepts you create on top. But on the other hand, you can't create those concepts without having the hardware. And so I think that's what got me excited about Gadgeteer, is to really cut out that hard part where you don't get credit for the hard part of building the hardware. And I think looking at the ACM Digital Library, I figured out there are really interesting spikes when people bring out new hardware and put it into research. So I looked at the CHI proceedings, and when Merle had the table out, I think 2002, 2003, around that time, a lot of research basically went there, and a lot of the sort of original papers on tabletop interaction were made with that hardware. Similar, when the Wii controller came out, there have been sort of workshops, etc. So a lot of people jumped on new hardware. Similar, I think the Kinect got something like 200 publications over the last year, references this technology. And so this shows a lot of people don't have the ability to create hardware themselves, but the moment the hardware is there, they use it. And so I think with creating a tool which enables people to go into new domains and create hardware is a good idea. When we look at the challenges for creating hardware, there are plenty of them. And we did a European project in 2000 to 2002. It was about creating a hardware platform that's extensible and which is easy for DIY. But what you really realize very quickly is you have these trade-offs. One trade-off, do you want to have something self-contained with all the sensors on board? You just take it out of the box, it works. Or do you want to have it in a way to stick it together? And similar, you want to have sort of size and weight that you can build a wristwatch. But then you're sort of making DIY, adding sensors, etc., very, very hard. And I think we have seen from James' talk at the beginning, those problems haven't gone away. And I think the requirements, processing, connectivity, sensing, actuations, they have stayed the same. But obviously, we have taken it to a new level with new processors. And I would guess some of those trade-offs in the next 2 to 3 years will be eased, because sort of putting more onto a board, putting more into an embedded system is just going to happen. If you look at what happened over the last 5 years with mobile phones. So we can really imagine to have sort of the full-scale board with all the sensors in a very small package. And by this sort of, it may be sort of, as we have seen sort of this explosion of use of mobile devices over the last year, we may see a change in embedded devices. Another area, so I think that's what I just said. Another area where we can learn from is the Arduino platform. And I think they're looking at processing, looking at the development environment is it makes it quite clear that without a good development environment, you're not getting anywhere. And I think the other thing which we see now with Arduino over the last years is that one size doesn't fit all. You need different sizes. And if you look around, what has developed, what the community has developed is quite sort of a wide range of devices, all the way to sort of having things you can design by parameter. And I think the development support is, if you look at Gadgeteer, it's well advanced of what we have seen so far. I think Bill had it in his talk, sort of code completion, all these things we are used to now on a PC, let you really forget that you develop for an embedded platform. And that's what I think we saw in the talk James had already. And I think in research, I just put in a few pictures of stuff we did and other people did. So I think with handheld devices, we have seen sort of a up and down. So around 98 to 2004, a lot of people built handheld devices. A lot of people built new wearable devices. And then with more and more powerful mobile phones and with an opening of the mobile platform, we have seen that everybody converges on the phones available. And I would guess there's a lot we can do in this domain which requires hardware. And I would guess there are a lot of opportunities ahead here. A second example is smart furniture, smart environments. And we have seen this morning one session on the smart home. And I think this is another area where new devices are very clearly needed. Otherwise, we don't really make a change to the environment. We don't really exploit the full potential. If you look to the interaction community, new input and output devices, here are two examples. And finally, also an example we have seen already from a workshop, the whole area of robotics. And I think there are a lot of other platforms out there. And what we see there, that those platforms can work together. And I think it's a lot about sensing, actuation, and the ease of creating systems. Skip this one. And now I want to move on to sort of what happens if we get this beyond the research lab. How would the world look like? But I first motivate us with a question. Who of you did bring a pen with them to Redmond, somewhere in the luggage? And I think if you read back sort of the UbiComp stuff, there is sort of this vision, we don't bring computers with us, we don't bring devices with us. And I think this test, who brings a pen, shows really that even sort of articles which are sort of penny value, we still bring because we don't trust that a good enough one is around where you need it. And so, but I think there's another reading into this. People like physical stuff. When we advertise conferences, we have tried quite often, if you put postcards on there or flyers, they usually don't go very well. If you buy an item like a little ball, a ruler, a pen, which is sort of similar in cost to produce than the postcard, people will sort of grab them and grab for their kids and whatever. It usually ends up somewhere in their luggage and they will sort of have to throw it away at some point. But it's really interesting. I think we are attached to physical things as human beings. We like to collect this. And there's another question. Can you imagine people driving those cars live on the same road? It's very likely if you go in suburbs, either they drive an SUV or a Porsche. And that shows that utilitarian properties of a product not necessarily define the product. So I think it's more about sort of what sort of car you can afford. I think the upper one I should have taken sort of a newer one. But I think the idea, people who usually drive an SUV don't have a dirt road to their house. And people who usually drive a Porsche don't live on a race course. And so the idea is we have a lot of products we use for self-expression. We show something about ourselves, starting from the haircut clothes to digital products. And I think this, again, argues we will have sort of a variety of products. And I did an image search on alarm clock. And if you see that sort of there is a big variety of alarm clocks. And I think if we look into the future, how those devices will develop, how they will sort of evolve, it's very clear we will have most of them as computing devices. They will be small computers with add-on functionality. And so at the moment you have, if you look at alarm clocks, you have a lot of companies being able to make an alarm clock. Probably thousands. How many companies are able to make sort of phones? It's a much smaller one. How many companies do make computers? It's again a smaller one. So my argument is my question is, what happens to those simple products in the future when they will become computers? Will there be 1 or 2 or 3 big companies who sort of, basically, will all of us in 10, 15 years down the road will have the major appliances from the same manufacturer, like we have with the phones? I think there are just a few around. So it's a really interesting question. And I would argue probably not. But to have this happen, we need sort of to rethink how electronic products are created. Skip this one. Another question, what is the killer app of your phone? So it's afternoon, so everybody's sleeping. So give me a few keywords. What are the killer apps on your phone? Email. Shazam. Text. Maps. And I think I argued Angry Bird. And I argued that the killer app of your phone is the phone. I think. So I think for me it's something. I tell you the story. If I leave home and I go to the train station and I leave my phone at home, I turn around. If I leave any of my other devices around, I don't turn around, because I figure out sort of email I can get on anyone's device. I just grab a student's device and say, yeah, find me a device in the lab. I think for all the things but my phone, I can sort of have this replacement. For the phone, it's about being reachable. That's why it's the killer app. So obviously there are other people who say, I'm using the phone very rarely, but you're not reachable if you don't have the phone. You always will find sort of means to replace access. So I think it's quite an interesting question. It's sort of, you can argue if it really is the phone, but it's an interesting thing to think what makes people really want a certain device, and what are the key features for a certain device. And we explored last year, last year, a little bit such devices which have big displays nowadays. So what is the difference between a sewing machine which costs 150 euro and one which costs 800 euros? Very simple mechanics. So for 800 euro, you get a sewing machine with much better mechanics. What is the difference between a sewing machine for 800 euros and 4,000 euros? Internet. It's the electronic bit which sits here, the internet. Why do they charge you 3,500 euro for sort of having a plug you can connect in, a website you can download? Because it really costs them that much. That's the interesting part, because they have small quantities, and for each of those devices, they really build a computer. And obviously, who has started to build a computer, there is a lot of cost involved in doing that. And so my argument here is the quality of a sewing machine is obviously sort of, you have to make, it has to work as a sewing machine. But it's very clear that 5 years down the road, 7 years down the road, you want to download new stitches, new patterns, whatever, on that machine. And so it's very clear you need a very easy way of creating a computer that's attached to something like, be it a sewing machine, be it a stove, be it a measurement tool, etc. And I think there is an interesting question. If it goes down the embedded systems route, like the Gadgeteer route, or if it goes the other way, that we just have a plug-in component for something like a phone, or if there is a hybrid device in between. But I think that's still an open question. If you look at apps nowadays, you have a lot of apps that have very few users, and very few sort of in the order of 1,000 or less. And you have still developers who are happy to develop them, because it may cost them something like 10 hours to write the app. If they get 1,000 users paying for it, it's for a lot of people sort of, it makes economically sense. We don't see this very much with physical devices nowadays.
Quick interruption. Have you seen Kickstarter?
Yes.
This seems to be their business model.
exactly. It's sort of and I think sort of somebody else could later give sort of a comment on Kickstarter and Gadgeteer in a way. And I think this is the thing, sort of getting smaller lot sizes out. And we see this in different areas, that you necessarily don't need to sell 1 million of something if you have a global reach. Usually, if you had physical products so far, you wanted to sell them in your hometown, and it's very hard to find, sort of, if you're not living in New York, sort of the right number of people wanting to buy it. But the moment you can virtualize the way you sell things, you have the opportunity to get sort of smaller numbers on a global scale, even if it's sort of a very alien product. And I will now sort of lay out a little bit how we imagine Gadgeteer in the future as sort of a material for physical apps. So the vision is you have a core where you have really sort of computing and technology inside. And if you're somebody who builds those products, you want to not understand too much about this one. And then you have something where you design the system, the UI elements, the thing like, the functional properties. And the idea is, and then you put it together into a consumer product. Now, how do you do that? I first go through a scenario. So the idea is we have a designer who has an idea for a really neat alarm clock. And he also sort of creates option for the end user to sort of customize this. And there are a lot of products out which are just physical, which you can sort of choose color, choose size. And then the customer goes to a web page, customizes the product, and orders it. And then what happens? The device body is printed. It may be printed at your place. It may be printed somewhere else. You get the hardware that exactly fits in there. You download the software directly in the hardware you buy. You stick the thing together. And then you ship it, or you don't ship it because you already assembled it at home. And if you look into this in more detail, it has a lot of interesting implications. So when you download software from somewhere, you don't go through a certification process. If you buy a toy car in the United States, which was fabricated in China, it probably had to go through a number of sort of steps to be sort of seen fit for sales here. So I think that's only one of the points. And you don't do this if you only sell 50 toy cars, you're not going through that process. You need to sell a lot. But if you don't have to go through this process because people will build it themselves, they just buy off the blueprint, that's one of the things which is going to change potentially how we do things. And I think 3D printing, laser cutting have been two technologies that are sort of enablers to this. And we have seen this in the lab. It really sort of changes that you can really, within hours, create the whole device, and not just the electronics, not just a paper mock-up. You can really create a device within hours. And this example was earlier shown, sort of the digital camera. And I find this a powerful way of showing to students how quickly you can create something. And the interesting point is, if you start building this digital camera, that's a digital camera, and then the idea, I want to do something that when you press the button, it does 2 pictures. I want to have a camera which looks who takes the photo as well as where it goes. Making this device will only add, you add another module, you add another 5 lines of code. So the interesting thing is, even with something very simple, you start out with something very simple, and then it's very quick that you get sort of into a whole new range of devices which you can build. And some of the challenges. What is missing to really make this work now? And I think at the moment we think a lot about sort of IDEs from a software engineering perspective, from a software perspective. And I think in the future we may think of an IDE as sort of a much bigger thing. It may be something where you really create products. It has a physical part to it. It has a software part to it. It has a hardware part to it. The other question is, how will business models look like for something like this? Sort of the whole distribution channel. Is it really something that like we see it on Shapeways and other things. You upload models, other people can download it, and you get a fee for the physical model. Can we imagine that we have sort of the physical products, or will there sort of intermediaries who build it for you? So you order it, and somebody packages up and delivers it the next day to you, that you don't have to have the 3D printer. I think those questions are still open and very interesting to explore. Another question with creating those things, we look at the moment in another project into domain-specific IDEs, where we really look for specific groups, for specific types of devices. So you could really imagine there is an IDE for creating digital cameras. And basically, when you start the Hello World program, it's already a digital camera. And then you can start adding further features, adding further triggers, etc. So it makes it much easier. So the hope is that within sort of in the short term, people who can now design a web page can also design a physical device. And I think besides the programming, one of the really hard things we see is 3D design. People really struggle with 3D design. And that's something I have no real good ideas. So we talked earlier about, and I think that the experience, a lot of people teaching have made this experience. People get very quickly around to understanding a laser cutter and building up things with a laser cutter. But the hurdle to get really into sort of doing 3D design seems much, much higher. One last point down there is the power options. And I think we have seen a lot with batteries now. And the moment we want to go for further devices, I think we should also think about further power options, which is, I think, it is easy. But the moment people have the option to choose from them, like solar panels, like mechanical devices, etc., would be quite interesting. And with this, I think we have a quarter of an hour still left for discussion.
Okay, thank you very much, Albrecht.